Awesome, we've done really well. We're already up to sequences. So if your brain needs a bit of a break, feel free to pause the video. But if you're happy to keep coming along for the ride, then let's get started on sequences. So sequences, we have our two types. Does anybody remember what our two types of sequences are? Hopefully it's thought of maybe something along the lines of arithmetic and geometric sequences. So sequences are a series of numbers that follow a pattern, unless it's a random sequence, which is kind of given away in the name, that it's a bit of a random sequence. But when we're talking about sequences, we're talking about a series of numbers that follow a pattern. So a sequence can be as simple as 2, 4, 6, 8, 10, 12. So we're following a pattern. All I'm doing is adding 2 each time. That's what I'm doing. And because it follows a pattern, we can actually predict the terms. So if we're given 2, 4, 6, 8, and I asked you to tell me what the next term would be, or the next few terms, you could probably tell me that the next few terms would be a 10, 12, 14, 16, and you could continue to apply that same rule of all I'm doing is adding another 2 because I can see that's the pattern, that's the rule that my sequence is following. So that's really interesting as well. And so to apply that in a bit more of a complex sense, all it comes down to is substitution into formulas, and some of which are on your formula sheet. So again, I just really want to emphasize to be super familiar with your formula sheet. So that you know what formulas you need to know, what formulas you don't need to know, and which formulas you need to know how to use. So again, go look up your formula sheet. Super helpful. A bit of sequence terminology. When we're talking about a term in a sequence, that's denoted Tn. So for example, T1, when n is equal to 1, T1, that's the first term in our sequence. If I was talking about T17, we're talking about the 17th term in the sequence. So, and each term, I covered that one. This is what I wanted to say here, and n always has to be a whole number. So if I said let n equal 1.5, so I can talk about term 1.5, we can't have that. It kind of just messes with the pattern, and we don't really do it that way when we're talking about sequences. So n always needs to be a whole number, and this is the example of the sequence I gave earlier. So this, all we've got to do is count along: term 1, term 2, term 3, term 4. Term 4 is 8. Super simple. This here, I missed that out there. But what I wanted to say there is that T1 is also known as A. So that's our starting point. So we can define that. Or sometimes it might be T0, but that's a little bit more depth than we'll be going into today. So A is another kind of way that we talk about our starting point. And our last little thing I'll draw your attention to is if we have like an ellipsis, like a ... that's just implying that the sequence goes on indefinitely. So arithmetic versus geometric sequences. This side of our Venn diagram is an arithmetic sequence, and this side of our Venn diagram is a geometric sequence. So let's have a look at the similarities and differences. First, the similarities, so what they share in common. Both sequences, I've cut myself off there. Both sequences have recursive definitions and general rules. So what's the difference between a recursive definition and a general rule? I'm so glad you asked. We're going to be talking about that. So this is the recursive definition for an arithmetic sequence. So the idea of recursion is we're taking one number and applying the rule to find the next term. Then we take that term, apply the rule to find the next term. We take that term, apply the rule, and we get the next term. And you get the picture. It can be a bit repetitive, but it's super helpful. We take term 1, we apply the rule, find term 2. Then we find term 3, 4, and so on. So we have Tn plus 1 equals Tn plus D. So this is a recursive definition of an arithmetic sequence. So what we're saying here is Tn plus 1, the next term, is equal to Tn, the term we're talking about, plus the common difference. So this is our rule. This is what we're applying every single time. So in my example earlier, 2, 4, 6, 8, 10, term 1 was 2. We were starting at 2. You can have any starting point A was 2, T1 or A was 2, and D, our common difference, was also positive 2 because we were adding 2 each time because I was adding the common difference every single time. And so that's how we've ended up with Tn plus 1 equals Tn plus D. And just to illustrate the substitution a little further, how this rule kind of works, if I was to say let n equal 1, then we'd have T1 plus 1 equals T1 plus D, common difference. So then we'd end up with T2 equals T1 plus D. So you can really see it coming out of what we're saying is the next term. To find the next term, all you've got to do is take the previous term and add the common difference. Whereas on our other side, our geometric sequences, we're not adding a common difference to find our next term. We're multiplying by a common ratio. So that's a really important distinction. So you can see here, I'll just pull up all our formulas. So you can see here, this is our recursive definition of a geometric sequence. We've got Tn plus 1 equals R, our common ratio, multiplied by Tn. So to find the next term, take the previous term or the current term we're looking at and multiply it by that factor, that common ratio, which is what we're multiplying it by every single time. This formula here is our general rule, or like our explicit definition of our arithmetic sequence. Because if, for example, I said find term 37, you're probably not going to want to use recursion to calculate all the way to term 37 because that would take up like your whole exam time and be super boring. You're probably going to want to find a way where you can skip straight to term 37, which is what you could do here. You could say let n equal 37, so then it'd be T1 plus 37 take 1 multiplied by whatever the common difference is, and then you're solving for Tn, which is term 37, and you'd be finding out what number is term 37 in the sequence. Coming over here, we've got our general rule for our geometric sequence. We have Tn equals A. Remember, A is the same as T1. It's like our starting point. A is T1, so that's our starting point, multiplied by R, which is our common ratio. And then we have n take 1. So, and because this is like to the power of n take 1, sometimes it can actually be a little tricky to solve for like the unknowns if you don't know what n is. So if you ever are trying to solve for n, it's probably best to just do it more by like trial and error and substitution. So what if we said let n equal 12 and you see if that kind of fulfills your rule? That might sound a little bit vague, but don't worry, I've got an explanation. I've got an example that'll help explain that further a little bit later. And then this here is how we find R. So it makes sense that if we take our next term and we multiply our common ratio by our previous term, then we get our next term. So it also therefore makes sense that if we want to find R, we can simply rearrange the formula and take the next term and divide it by the previous term to get our R value. And then we can do the exact same over here for arithmetic sequences. If we simply rearrange this formula to isolate D, we can also solve for our common difference. So again, our arithmetic sequence, we're adding a common difference each time. In our geometric sequence, we're multiplying by a common ratio each time.